So, what is partial correlation? How will it help us understand our data better and eventually build better regression models? Stick around and find out. Hello and namaste. My name is Brandon and welcome to the next video in my series on basic statistics. If you are new to the channel, welcome. It is great to have you. Thanks for joining us. If you're a returning viewer, it is great to have you back. Now, if you like the video, please give it a thumbs up, share it with classmates, colleagues, or friends, or anyone else you think might benefit from watching. Now, in the description below, you will find two important links. The first link is to the files you can download to follow along. The second link is to a table of contents for all of my video playlists. So, if you want to learn something else, follow that link and you'll see that list there. And of course, if you have not already, please hit that subscribe button and bell notification. So now that we are introduced, let's go ahead and get to learning. So what should you know or have a basic understanding of before beginning this video? Well, first, you should know what a basic correlation is. So it is a numerical or quantitative measure of the relationship between two variables that is on a range of -1 to +1. This is basic descriptive statistics. You should also have an idea of linear regression, especially the concept of R-square, which is the amount of variance explained in the dependent variable. And finally, you should have a basic understanding of how Venn diagrams work for the visuals we're going to do. Now, you might have seen these in previous math classes, say a finite math class or a linear algebra class, and you still have nightmares about them. However, it's just a series of overlapping circles where we're trying to find the area where they overlap. And we're going to walk through all of these step by step. But this is the technique we will use for the visuals, so you should have a basic understanding of at least what they are. So first, some foundational concepts and maybe a metaphor or two. So let's assume we have a set of independent variables, or IVs. Let's put them over to the side on the left. And one dependent variable we'll put over here sort of on our imaginary right. Now, if the IVs are not correlated with each other, then each IV to DV relationship is much less complicated. And here's sort of an example I can think of in real life. Let's say a friend of yours invites you to a coffee shop or something. And they say, I want to invite two of my other friends, say one from work or a childhood friend or something like that. You all show up and the three of you who are invited don't know each other. The only relationship you have is to your mutual friend who invited you. That's a case where it's IV to DV, IV to DV, and then IV to DV with the IVs, in this case the three friends, who don't know each other. So back to math. Now in that case, we look to the magnitude of the pairwise or one-to-one IV to DV correlations, or when we get to regression, the standardized regression coefficients. So the way to sum that up is that if the IVs are not related to each other, then we're just looking at IV to DV, in this case in 3 instances. Now, if the IVs are correlated, it becomes more complicated. So let's go back to our example before. Let's say everyone shows up to the coffee shop, but it turns out of the 3 friends your friend invited to the coffee shop, you happen to date one of them 3 years ago. Well, that could be awkward because now there is a friend-to-friend or an IV to IV relationship that has to be taken into account. So that changes the relationship between the mutual friend who invited you, or it could. So think of it that way. So if the IVs are correlated, it becomes more complicated because some of the IV to DV relationship may actually come from other IVs. There could be a shared relationship there. And that's what we're going to tease out when we're talking about partial correlations. So what is a partial correlation? We often start with asking a basic question. What is the relationship between two variables while controlling for the effects of other variable or variables? It could be more than one. However, when there are multiple independent variables, it is possible that other independent variables might jointly explain the relationship with that dependent variable. And of course, they could be related to each other. For example, let's say the variance in blood pressure might be highly explained by a person's age, but if we add in, say, if they smoke or not, and the amount of alcohol they consume, the relative importance of age to blood pressure might change, and it creates IV relationships in the process. For example, for the two we added, is someone who smokes more likely to consume more alcohol? The data suggests that they do. Is someone who is older more likely to smoke? Don't know. Is someone who is younger more likely to consume more alcohol? Don't know. But now we have age, smoking, and alcohol to consider when trying to explain variance in blood pressure while also accounting for the relationship between age, smoking, and alcohol. So we want to tease those apart. So partial correlation runs from -1 to 1, just like a regular correlation. And that allows us to examine the correlation between two variables while controlling for the effects of other variables. This is the partialing out step. So the variables partialed out also have another name, covariates. Now note, when it comes to notation, that you will often see the partial correlation written with the Greek letter rho, which looks like a oddly shaped lowercase p. However, in this video, to keep things easier, we will use PR for partial correlation, and you will see that in some textbooks. You'll see both. But we're going to stick to PR, which is a bit more intuitive for our uses. So 3 considerations. So in this video, we will visually examine the correlations and partial correlations using 2 independent variables and 1 dependent variable, just to keep things easy for this basic introduction. So number 1, we will examine the overall relationship of 1 IV to the DV. So 2 cases of that relationship. We will look at the distinct relationship of 1 IV to the DV, controlling for the other IV. This is the partial correlation. And then we'll examine the correlations and partial correlations of all the IVs with each other. So we will focus less on that. We're going to stick to the IV to DV relationships, but we will look at those towards the end. So for items 1 and 3 on this list, we create a matrix. And for item number 2, we create a matrix of partial and semi-partial correlations. Now I put an asterisk by semi-partial because in a video or 2 from now, that's kind of where we're going. So a partial correlation is a step along our understanding towards understanding semi-partial correlation, which will then lead into how we build regression models. So we're just kind of going step by step by step. So we'll get to semi-partial correlations here very soon in the playlist. So what about correlation and R squared? Let's start at the very basic level here. Let's say we have 1 dependent variable we'll call y here, and 1 independent variable we call just x1. And let's say hypothetically that the R square for that relationship when we do a linear regression is 0.2025. Now, what do we mean by that? Well, actually, that R squared is the area of the overlap. The area of each circle is 1. Where they overlap, that's the R squared. In this case, I just picked a random number. It's 0.2025. That's how we can visualize the R squared. Now, if we turn that into an actual square, it would look something like this. So we could take the square root of 0.2025, and we get an R, which is a correlation of plus or minus 0.45. Now, it could be negative 0.45, or it could be positive 0.45. We would have to actually look at our data, look at the slope of the regression line, and a scatter plot to figure out if it's plus or minus. It could be either. But in this case, we'll just assume that it's positive. To summarize, the area of overlap between these 2 variables in a regression is the R squared value. We can pull that out, actually put it into a square format, and there we can see the R squared and the R, which is the correlation. And as I mentioned, check the sign in the regression formula to see if R is positive or negative. Let's look at one extreme. Let's say we have our dependent variable y on the right, our independent variable x1 over on the left, and the R squared is 0. Unlikely to happen in most situations, but let's just say hypothetically it's 0. They do not overlap at all, they are completely separate. And of course, our R, our correlation, would also be 0. So this is one extreme. What about the other extreme? In this case, they overlap completely. So in this case, the R squared is 1, because remember the area of the circle is 1. And therefore the R, or the correlation, is either +1 or -1. So those are the two extremes. We will likely not encounter those two extremes at all, but it's good to know sort of what we're going from in either end of that extreme. So for this lesson, we're going to use part of the MTCARS dataset that is built into R/RStudio. You do not need to know R to watch this video or understand the concepts we will be learning. We're just using this dataset for the sake of simplicity. And you can download all the files in the description below. So from MTCARS, we're going to use 3 variables. We're going to try to explain the variance in MPG using what's called, I'm going to call it DRAT, and HP. So miles per gallon, which is MPG, that's going to be our dependent variable Y, is modeled by rear axle gear ratio, which I'll explain in a minute. I'm going to call it DRAT for X1, and engine horsepower, which is HP, X2. So very quickly, I don't want to sound like James May from Top Gear or Grand Tour, which I love by the way, but horsepower is just the power of the car, so the engine horsepower. DRAT, or the rear axle gear ratio, is a bit harder to explain, but I'll keep it very simple. So the rear axle gear ratio in a car determines at the end how many times the wheels rotate for each time the engine rotates. So let's say that once it goes through all the gears and everything, the engine turns 1 time, and that causes a turn in the wheels, say 3 or 4 times. That's the rear axle gear ratio. That's basically what it means. So we're going to try to explain the miles per gallon, or the gas mileage, using the rear axle gear ratio and the engine horsepower. So first, 1-to-1, what's called zero-order correlations. When you do a basic correlation with a data set, and you're looking at variable Y to variable Z, or whatever it is, just a 1-to-1 correlation, that's called a zero-order correlation. So you might see that in a textbook or something you read. So here is our correlation plot. Let's take a look at this for a second. Down below, we have MPG in the first column, and then we have HP, or horsepower. This is the first row. Then we have DRAT, the drive axle ratio, the second row, and then the top row, we just have our ones that go down the middle. So what do we make of this? Well, it appears there's a strong, so 0.68 correlation between DRAT and miles per gallon. So it seems that higher rear axle gear ratio is related to higher miles per gallon. And this should make sense. So what I said is that the rear axle gear ratio, that kind of determines how many times the wheels spin for every time the engine spins. Well, if the rear axle gear ratio is high, that means that for the wheels to make a turn, the engine has to turn less. And if the engine is turning less, that means you're using less fuel. If you've used a manual car, that's like going into 5th gear. You'll notice that when you're going into 5th gear, that the car goes faster, but the engine is turning the same rotations. That's because the wheels are turning more each time. So you actually get better gas mileage when you have a higher ratio like that. So there's a strong negative, so negative 0.78 correlation between horsepower and miles per gallon. So more horsepower seems to be related to lower miles per gallon. Now, that makes sense. Cars with more power, muscle cars or exotic sports cars, whatever else it might be, that have a lot of horsepower, create that horsepower by burning more fuel and air. So the miles per gallon is typically lower. And then finally, I'm going to point this out, but we're not really interested in this at this point. There is a moderate negative, so negative 0.45 correlation between DRAT and horsepower. So more horsepower is related to lower DRAT. And just quickly, the reason for this, these cars are from the 70s, so this is a bit old, but more horsepower cars are sportier cars. They would tend to have a little bit lower gear ratio, because they are meant to run at higher rotations in the engine, and that makes them a bit more sporty. And actually, I have a car that kind of works like that. But that is that relationship. And I don't want to go into that because we're really focusing on horsepower DRAT going into miles per gallon. Okay, so let's look at our first R squared. Let's take each of these one by one. So the R square for both single IV to DVs. So two simple regressions. Let's look at DRAT as it explains the variance in miles per gallon and horsepower as it explains miles per gallon. So 1-to-1, two regressions. So these are basic regressions you could do in Excel or whatever stat software you use. Nothing complicated here. So in our first case, where we're explaining the variance in miles per gallon using the drive actual ratio, we have an R squared of 0.464 and a correlation, which is the square root of that, of 0.6812. In this instance, 1-to-1, DRAT seems to explain about 46% of the variance in miles per gallon. Now horsepower has an R squared of 0.6024. So in this case, it appears horsepower explains about 60% of the variance in miles per gallon. Again, just looking at those 1-to-1 in each case. Now, if you remember, the correlation was negative in this case. So you take the square root of that and you have negative 0.7761. So the first thing we do here, just to kind of get the R squares, is we do a regression for each 1-to-1 relationship with the dependent variable miles per gallon. And finally for R squared, we run a regression with both of them. So a simple multiple regression where we include DRAT and horsepower. So you can do this in Excel, whatever stat software you have. The R square here is 0.7412. Combined, DRAT and horsepower explain about 74% of the variance in miles per gallon. Now you will note that 0.7412 is higher than both DRAT alone or horsepower alone. And remember, the maxim for multiple regression was that the R squared will never go down when you add variables. It can stay the same or go up, but it will never go down. So in this case, it went up to 0.7412. So let's quickly start our visuals and visualize the R square for our first 1-to-1 regression of DRAT in miles per gallon. Here we have our dependent variable of miles per gallon here on the right and DRAT here on the left. So we know from our previous example that the area they share is the R squared. And in this case, it's the letter A. Now D is the unexplained variance in miles per gallon. To focus on miles per gallon, let's take away the other part of DRAT. And now we're looking at just our dependent variable. So we know that the R squared is 0.464. That is there in the A. So we know that A plus D has to equal 1. The area of this whole circle is 1. A is 0.464. Therefore, by subtraction, D is 0.536. The R square of this regression is simply the area of A divided by A and D together. And this is very easy math. It's just asking us what proportion of this circle is taken up by A. So we can just do the very simple math. Very easy, and we get what we have before of 0.464. And we take the square root of that to get R, which is the correlation, and we have 0.6812, which is what we had before. So you kind of see how this works. So the R square is the overlap, and we add those together. We're looking at a proportion of this entire area, that's the overlap, and we come up with our R squared of 0.646 and our correlation, or our R, of 0.6812. Now the same thing for horsepower. So we'll take away the other horsepower we don't need. Now we're looking at MPG and horsepower. So the R square here is 0.6024. That's the area of C. So that C plus D equals 1. C equals 0.6024. D, by subtraction, is 0.3976. So the R squared is just C, the area there in the yellow, divided by the whole thing, which is C plus D. That's 0.6024 over 1. And we take the square root, and we get our R squared. Now remember that the R is negative here, so we would actually write this as negative 0.7761. What about both independent variables? So there we just did MPG and DRAT on its own and MPG and horsepower on its own. Now what if we put everything together? Well, it looks something like this. And this is very psychedelic with colors and everything. But what we're going to do is figure all this out so we can find out exactly where the overlap is, and that will lead us to our partial correlations. So we know that A plus B plus C plus D has to equal 1. That's the area of our dependent variable over here where the y is. So A, which is in the purple, is the variability in y explained by x1 only. So you can see that the area of A is only where x1 and y overlap. C is the variability in y explained by x2 only. So you can see that C, there in the yellow, is where y and x2 overlap. And then B is the variability in y explained by x1 and x2 jointly. So that's where they overlap with each other. They all three overlap. Now, what we're going to have to do is figure out the values for A, B, C, and D. And that's what we're going to work towards as we go. So we take out anything that is not in our dependent variable, take that out, we take this out, and this is what we're really focusing on. So the entire area of this circle is 1, and we want to find out the values for A, B, C, and D, because that will help us get to our partial correlations, and semi-partial correlations for that matter. So first, let's look at the R squared for x1 to y, our dependent variable. So we take away everything that is not in our dependent variable y. So we do away with everything else and we focus on just this. So the R squared is where A and B overlap with y. Remember, that's where x1 was. So we're interested in the area that is represented by A and B. So think about this. The area of that R squared has to be 0.464. We already figured that out. Well, mathematically in this circle, that is A plus B, which is there in the purple and the gray, divided by the whole thing, A plus B plus C plus D. That is the R squared for x1. R squared for x2. Again, we take away everything that's not inside our dependent variable y. What will this be? Well, this is going to be the area of B and C, because that was part of x squared that we just took away. So mathematically, that is C plus B, there in the yellow and the gray, divided by the entire thing. And in our case, that is 0.6024. So that's how we visualize the R square for each 1-to-1 relationship. So x1, and then here in x2. All we're doing is some simple math and visualization. Now, what about both of these? So we take away everything that's not interdependent variable. Then we have our combined model where we have x1 and x2, so DRAT and horsepower. And that we know is all three of these areas, A, B, and C. So that value has to be A plus C plus B, or A, B, C, whatever, divided by the whole thing. And remember, that R squared was 0.7412. So all we're doing is putting our explained variance where things overlap. So x1 to y, x2 to y, and then x1 and 2 combined to y. And we use the R squares we got from our simple regressions we did before. So let's solve the R square puzzle. So this is a finite math problem, and we want to find the actual values numerically for A, B, C, and D. So we know that A plus B plus C plus D equals 1. That's everything there in the orange circle where they overlap. We know that A plus B equals 0.464. That is the R squared for DRAT. We know that B plus C equals 0.6024. That is the R squared for horsepower. That's the B and C areas there. We also know that A plus B plus C is 0.7412. That was the R squared for the combined regression for horsepower and DRAT. Now we know that D, by subtraction, is 0.2588. And that's just simply 1 minus 0.7412. So we got that one. Now how do we find B? We're going to use the addition rule of probability. So remember this? You probably saw this in math class at some point. It's not that hard, trust me. So this says that the probability of a union, which is like a total area, so in this case, it's going to be ABC, is equal to the probability of A, which is one of the slices, plus the probability of B, which is one of the other football-shaped slices, minus the intersection. This is going to be the probability of A union B is ABC. Probability of A is A and B. Probability of B is B and C. Then we're going to subtract B because we're counting it twice. We put some numbers to this, and we have 0.7412, that's ABC, 0.464, that is A and B, 0.6024, that's B and C, but we have to subtract to B because we counted it twice. This is just a very simple, math problem. So we do all the math out, and it ends up that B is equal to 0.3252, A is 0.1388, and C is 0.2772. And we just did that with some math. Once we figured out what B was, we could go back up to the top here and substitute B in wherever we have A plus B or B plus C, do the subtraction, and we'll get just A and just C. D we already had, B we figured out. Those are the four values, the four R squares for A, B, C, and D. Now the partial correlation for X1, which is DRAT, and Y, which is MPG. Let's take out everything that's not interdependent variable again. So we'll fade those out. Now at this case, we're at the R square stage, remember? But now we want to go to partial R squared and partial R just by taking the square root. So for X1, we have to partial out what? Think about it. From here, we want to partial out anything that's not X1, right? We take away B and C. We chomp out anything that was part of X2. So the partial R squared is A divided by A plus D. So A plus D is the total area here, and then A is just a proportion of that area. See the difference? And of course, we take the square root to find the partial correlation. So we have partial R squared here and partial correlation over here on the right. And we partialed out anything that wasn't part of just X1 and the dependent variable. So we partialed out X2 from both X1 and Y. So for X2, the same process. We will fade out everything that's not part of the dependent variable Y. This is where we are at R squared. Now we want to partial out everything that's not X2. So what's going to fade out here? Well, it's going to be A and B. We partial out everything that was part of X1. So this is C divided by C plus D. Take the square root to get the partial correlation. And we partialed out X1, that's sort of this bite out of the side of A and B, from both X2 and Y. So that is what partial correlation looks like in these Venn diagrams or circle diagrams. So with some simple math, it looks like this. Fade everything out. So we want to find out the partial correlation here for miles per gallon and DRAT. That's our first variable. So remember, it's A divided by A plus D. We calculated A as being 0.1388. D is 0.2588. So this is very simple. And we end up with a partial R squared of 0.3491. Now we'll take the square root of that, and we have 0.5908. And there is the partial correlation between X1, which is DRAT, and miles per gallon. Now if you look here, partial correlation is written as something dot something. Before the period or the dot there are the two things you're correlating. In this case, it's Y and X1, which is DRAT and miles per gallon. Then you have a dot, and then after the dot is everything you're partialing out. So in this case, we're partialing out X2. And we could have X3, X4, X5. We could have multiple variables to the right of that. So we have whatever we're correlating on the left of the dot, and then whatever we're partialing out to the right of the dot. So the partial correlation between X1 and Y or DRAT in miles per gallon, is 0.5908. Now for x2, we'll take out everything that's not part of our dependent variable. Partial out x1, so we're left with c and d. So the partial r squared is c divided by c plus d. C equals 0.2772. D is 0.2588. Do that very simple math. We have a partial r squared of 0.5172. Take the square root of that to get to our partial correlation. And remember, it's negative, so it's negative 0.7191. So negative 0.7191 is our partial correlation between horsepower and miles per gallon. So finally, let's confirm our visuals mathematically. So using our visual method, the partial correlation between y and x1 while partialing out x2, so in this case, the partial correlation between miles per gallon and DRAT while partialing out horsepower was 0.5908. Now, for the partial correlation between miles per gallon and horsepower while partialing out DRAT, which was x1, is negative 0.7191. Now, if I go into R and do the partial correlations, this is what we get. And you can see that they match. They are the same. So the partial correlation between DRAT miles per gallon is 0.59. That's what we have over here on the left. And between miles per gallon and horsepower is negative 0.72. That's the same thing we have over here on the left, just with rounding. So some final summary statements. So while the zero order correlation between miles per gallon and DRAT was 0.6812, when controlling for the effect of horsepower, the partial correlation between miles per gallon and DRAT was a little bit weaker at 0.5908. And while the initial correlation between miles per gallon and horsepower was negative 0.7761, when controlling for the effect of DRAT, the partial correlation between miles per gallon and horsepower was slightly weaker as well, at a value of negative 0.7191. So both one-to-one correlations, the zero-order correlations, changed into first-order correlations, that's our partial correlation, and each of them got a bit weaker in the process. Now, why do you think that is? Remember, there was a relationship between DRAT and horsepower. It was like negative 0.45 or something. So that makes sense. So the contribution and the relationship between each of these went down a little bit. They got a little bit weaker because there was already a pre-existing relationship between DRAT and horsepower. So therefore, it would appear that horsepower was affected less so than DRAT when controlling for each other with respect to miles per gallon. Now, the semi-partial correlation will tell us even more about the independent variable to dependent variable relationship. And we will get into semi-partial correlations soon. So the next video in this series, I'm going to go into R to show you other methods for getting the partial correlations, including correlations among residuals. So this was a very visual way of looking at partial correlations. The next video will be a bit more mathy. All right, so that wraps up this video on partial correlations, a visual introduction. So I hope you found this video helpful. You found the visuals helpful in understanding how everything is put together, so you can kind of see how variables are related to each other and how they're related to each other once you take into account another variable or set of variables. So you kind of have that visual in your head. All right, thank you very much for watching. I appreciate you spending your valuable time with me, and I look forward to seeing you again in the next video. Take care. Bye-bye.